Okay, I think we can get started. Today's house, given by me, my name is Pin Liu. Yeah. Well, it was not, basically, we didn't find a speaker for today, so I volunteered to do one. So, yeah, about me, I got my BS in China back in over 20 years ago, probably. Then I went to Hawaii for 8.5 years there. Then came over here in the late 2009. And recently I was promoted to research assistant professor, which is good. I think I'll give this one as a, late seminar for that. But anyway, as you can see the title, it's about extreme droughts and heat waves. I actually did not do this much too long ago, but I'm interested in this topic, so I'll give you some of the results or thoughts, and let's get started. The extreme events are very costly, such as hurricanes, like droughts, heat waves, tornadoes, etc. According to the National Centers for Environmental Information, there has been 196 weather and climate disasters since 1980. Each one of them is about $1 billion, and totally they cost $1.1 trillion, very costly. Here's accumulated extreme events for each year. We see that during 2011, which is the toppest, we had about 16 events of these $1 billion extremes. Among these events, hurricanes or tropical storms, cyclones, are the most costly. They cost over 50% of the total, 1 trillion. And the second place we can see here is the droughts. They cost about 20%, which is very costly. And they are also very deadly. Among these 23 events only, there are about 3,000 deaths. Extreme heat waves, that could be even more dangerous, particularly to the elderly. Here's an example for the 2003 Europe heat wave. It lasted for about 2 months. During that period of heat waves, over 20,000 were dead because of that. And the record temperature was the warmest for about 500 years. That's a record for 500 years. And the total cost was about 13.1 billion euros. It's about $20 billion by then. So the question is, how and why did these extremes occur? Now, when, where, and how severely will they occur again in the future? So we are going to discuss these questions today from the statistical point, not from dynamical or simulation or prediction or projections, although those topics are very hot as well. But today we're only go through some of the statistical results and approaches. So here's the outline. I firstly need to introduce you some of the indices to describe the droughts and heat waves. And based upon these indices, we can see the extreme droughts and heat waves. Then I have to introduce you some of the statistical tools, particularly to deal with these extremes, which is called the generalized extreme value theory, including stationary or non-stationary. And then we're going to try to connect these extreme events with persistent atmospheric patterns, such as the NL, which is North Atlantic Oscillation, PNA, the Pacific and North America teleconnection pattern. Most importantly, I'm going to show you some of the recent results from our study about blocking and persistent open ranges. And also the trend. Trend is not the typical persistent pattern, but it's already there. So we're going to include that as well, particularly in the analysis of temperature and also the droughts. But we're not going to discuss anything about NSOL, which is important, of course, or AMO, which is the Atlantic Meridian over multi-decadal oscillation, or PDO, etc. Those phenomena are also important, but they are basically Earth interaction or purely from the ocean side. So, but we're not going to discuss them today because of time. And then the key question we're going to ask is how the persistent atmospheric patterns listed here would affect the extreme droughts and heat waves statistically. Now, first, I'm going to introduce you some of the indices to describe droughts and heat waves. The drought has numerous indices since the very beginning of the science. There are 3 of them I would like to mention here. It's called the PDSI, SPI, and SPI. Starting with the PDSI, its P is for Palmer. It's a very famous scientist. He designed this Palmer Drought Severity Index, which is PDSI, back in 1965. And this index incorporates temperature and precipitation both. And he used these 2 fields for empirical water balance. So we know that droughts occurred because we have deficit in precipitation, so we need a balanced model. He used these variables to build an empirical water balance model, and then based upon data from only several U.S. stations. It has a time scale about 9 months, and also designed for the agriculture drought. So in some sense it's limited, but it's also mostly widely used. The computation of PDSI is very sophisticated, mostly from its demand of water. Because again, we only based upon the temperature itself, we got to build up an empirical model to describe the demand. So based on a recent paper to do that, here are the steps. We're not going through each step, of course, just to show you how sophisticated it is to compute this index. And here is what we can see for the California record drought back in 2013, actually starting from 2010 all the way to recent years, even to this year. There was a drought, very severe. This is a snapshot, or that month is a monthly PDSI snapshot for the April 2013 over Western states. Over here, California, I'll draw this box later to show you the average evolution of time series. We see that the values could be lower than -6. For the PDSI, it could be as low as -10, describing the most extreme drought. For here, already lower than -6 means it's very drought in that month. Here's a time series from that box I just showed you. Also monthly, starting from 1895 all the way to last month. It's monthly. We see the periods over here. It's the most severe between 2010 and 14. We also see in 2015 as well. So we're interested in these extremes, not necessarily near 0, but they're really extremes like this year -4 and this year -6 or even higher. For the PDSI, because it's based on several stations in the United States, so it's really not so easy to compare the conditions with other regions. So there's another variant. It's called the self-calibrating PDSI. It basically includes the local climate characteristics to estimate the empirical constants, which is understandable. So that sense makes the index more comparable. The result basically similar to the original PDSI in the United States. So we're not going to repeat that index here. The second drought index here I want to introduce is the SPI. It's totally based on the precipitation, named Standardized Precipitation Index, developed by McKee back in 1993, and adopted later very soon by the WMO for international comparison of the drought condition from the precipitation itself. And computation is really easy. We just get a cumulative precipitation, feed some distribution, such as a type 3 Pearson distribution with 3 parameters. Then we get a cumulative probability distribution. Then we transform it to a normal distribution. Then we get a SPI. So statistically, it's straightforward to get this index. But again, drought is not just about deficit in precipitation. It's also about temperature. So we need the temperature as well to define the drought, even if it's not complete. So recently, back in 2010, there's a new index which is called the SPEI, Standardized Precipitation Evapotranspiration Index. As you can see, it includes both precipitation temperature at the same time. The calculation of this SPI pretty much similar to the SPI, except we're going to again deal with the vapor transpiration from the temperature data. So that's probably about this SPI. SPI, when they designed this one, they compared this index with the PDSI and SC PDSI. So they concluded that only these two indices, SC PDSI and SPSI, could possibly reflect the global warming trend. So anything you will see later based upon the PDSI itself, if there is any change or trend, is probably coming from the precipitation deficit, not necessarily the temperature. Because again, the PDSI was believed is difficult to consider the global warming trend. This as a background. So next, the indices to describe heat waves. Heat waves, again, it's really not about temperature itself. Just like we're going to spa, take sauna, with relative humidity very high, we could get a very hot even when the temperature is low. So apparently we need to combine both temperature and also the humidity as well to consider the heat wave. So this comes with the concept is or index based upon the apparent temperature. Based on this apparent temperature, we'll have two indices to describe the heat wave. The apparent temperature basically just like this form, combining temperature and vapor in this format as a vapor pressure. So it's an empirical index as well formula. Adopted by NCEI to describe the heat stress. This is one form. Another one very similar, but consider the wind speed. As everybody can feel, if there's strong wind, even if it's hot, it becomes not that hot if you have some wind. So once wind speed is larger, we get some more heat stress. So this is a formula adopted by the Australian Meteorology Bureau. A third one, which is used by NWS here, it's a heat wave index. It's called HI. So they basically also based upon regression formula, starting from ADF. Over here, it's very sophisticated, but also based upon regression, and also give some adjustment based upon the relative humidity. So again, it considers both temperature and the relative humidity. And as an index, it covers the whole range of temperature, such as lower than 80 degrees, we use this formula. Okay. Based on this index, the NWS describes several level or degree of heat. For the caution in yellow, basically when the heat index is above 80, right? Yellow, and then some red, light red above 91 degree, which is about 22.7 degrees Celsius. It's called extreme caution. Then above 102 F, which is about 38.9 degrees Celsius, becomes danger. Extreme danger always up near 130. We see that, and we're interested in these extremes, not just these danger or extreme caution occasions. But as a background, next I'm going to show you some of the distributions in terms of the extreme caution and danger in that scale. Here's the average maximum heat index in July and August, which means we have 2 months daily. The index, we find the maximum. And then for each year, we have one maximum over each location or grid point in this case. Then we get the average during 1961 to 1990. We get this map. This map just shows us the distribution over the North America, or particularly the United States, the distribution of this extreme heat, because again, they're maximum. Not necessarily everywhere are danger, but they are the maximum. So basically we see over the central United States over here, this part, it's very, very hot during summer in terms of the heat index. This is a background. And this is a difference, we see the trend difference between the recent decade compared to the climatology. Again, we see it's getting much warmer, much worse for the extreme heat index. Especially if you look at the central United States over here, we get about 4 to 6 degrees. Along the Gulf, we see even hotter climate. In the east, we see hotter. But our focus later will be on the central. I'll tell you why later. Here's a time series for the central United States to show you, again, it's a maximum, but at the maximum, again, maximum of the maximum. Maximum first, the maximum of the July to August, then maximum is over that region, so 2 maximums. This is a trend. There's a trend, of course. Also, we see an extreme. Back in 2012, I believe, or 11, very hot in that season. Not only the temperature magnitude itself, but also the persistent days in terms of heat waves. Okay, we sometimes are concerned about 1 day heat wave. If it's longer than 1 day or 2 days, 3 days, it's really a problem. Very hot, very difficult situation for many people. So here's the days in terms of hot days, longer than 91 degrees in that 2 months. How many days we can count during the past for the target during those 30 years, which means during each year we count the days above 91 degrees and we average them. So we see that about 60 days, nearly every day in those 2 months, we see very hot days over the central United States. Again, this is as a background. There's also some trend. The trend is obvious in the western United States during the recent decade compared to the climatology again. We see about 7 days in the west, but very slight change in the central United States. Some change, about 4 to 5 days in the eastern United States. So for the central United States, we see the increase in temperature magnitude, but not much in the persistent days. So in that sense, when we talk about extreme in the central United States, we consider only one. That's the magnitude of temperature itself, right? So this is one reason. And to give you more background, this is the average of the large continental. For example, North America in red, we average everything, every grid point in North America in terms of the extreme, in terms of days, like hotter than 91 degrees. So we get the distribution or the evolution from 1950 all the way to September 2016. So red, we see it's not much, there is fluctuation, but not much trend during the first several decades, but then we see some trends up. And then for Europe, we see even stronger trend. And there's extreme over that year back in 2010, which was another extreme all over the Europe, not necessarily just Western Europe. And for the Asia, there's also some upward trend. So the background here, this is an aerial average again. For danger days, we also see some similar trends upward, although the overall trend is about 4 days smaller than the lower temperature. Okay, after this index, we can see that for the extreme droughts and extreme heat waves, we care about first the magnitude, second the persistence. Persistence is the key factor. Any of these two extreme events, if they persist for some time, we need to be very concerned about those persistence. So in terms of persistency, we probably can associate them with the persistent atmospheric patterns. This is because the persistent atmospheric patterns could be more directly cause these persistent extreme events. So next will be these persistent atmospheric patterns. 3 are listed here, including the trend, which will be embedded in the time series itself. So first, the PNA. PNA is the Pacific North America teleconnection. Okay, so it really tends to impact the precipitation in the western United States, which covers California. So that's the reason we are concerned with the PNA pattern. But it does not notably affect the surface temperature variability over the North America during summer, which means if we see central United States heat waves, we probably cannot attribute to the PNA pattern that significantly. So to simply see the PNA, here's a positive pattern, here's the Western United States. When it's positive, we have positive anomalies over the United States. So this is a very easy way to remember the positive phase of PNA. Whenever there's an anomaly in terms of 500 millivolts potential height, we have a positive anomaly in the Western United States. So that's a positive phase. You can imagine whenever we get a positive anomaly over the Western United States, we probably will see a dry condition, give us less rainfall, warmer temperature. This is in January. This is in July, indicating the summer season. We basically see the PNA pattern or the signal is much weaker than during the winter season. In that sense, we probably can see less impact from the PNA pattern as disclosed before. As indicated, for the precipitation correspondence with the PNA positive phase, here's the deficit as minus values in January, which is in winter season. But in summer season, we see the signal is very weak, so very little impact. In temperature, we see the red here is warmer, basically because of the positive anomaly itself. Again, in winter, we see very little signal over there. So this is the background. Here's time series, daily time series. Steady time series starting from 1950 of PNA all the way to September this year. So we see during the California drought back several years, the PNA pattern or index itself is mixed. Okay, this is a background. When we want to do tribute the drought in California to the PNA, we've got to be very cautious because the pattern itself or index itself is mixed. This is the background, but still we have the extreme events more than just a couple of years ago. We have more historically, so that means the PNA could contribute to other events. That's what we need to look at later. The next pattern is NAL, which is well known. It's a North Atlantic oscillation. It's a north-south dipole of anomalies. Again, to remember the positive phase, the anomaly in the south is always positive. Again, if you just look at the anomalies over the United States or North America, it's positive. So this is a positive NAL phase. Again, during the positive NAL phase, we see positive anomalies over the United States give us warmer, drier, warmer conditions. This is in winter season. In summer season, it's pretty much similar pattern, but with smaller magnitude, meaning that during summertime, NAL might have some impact, but at a lesser degree than the winter seasons. This is a precipitation. In winter season, very little signal from the NAL, but there's some in the eastern United States getting drier. The temperature, as said, in winter we see positive anomaly over most southern United States and eastern United States during the positive NAL phase. But during summer, we see north central United States, we might see some positive, or northwest. But in the south, we might see some cooler temperatures. But that's the overall statistics, which means we get a long-term statistics, not necessarily applicable to the extreme events we're talking about. Here's a time series for the NAL during daily again from 1950 all the way to last month. Again, we see that it's mixed during the past California drought. So we cannot get a direct conclusion that NAL contributes to that drought or heat wave itself. So we need some statistics. The third one, I think is the most important one, is the atmospheric patterns in terms of blocking. So it's persistent. Blocking, we heard this word before. Well, dynamically, it's just characterized by dominant westerly in the mid-light as we know that, is replaced by easterly somewhere, somehow. So this coincides with the reversal of the pressure grades, right, along a longitude, based on the geostrophic balance, which is understandable because, again, the blocking itself has a very large scale. And also it has a barotropic feature, which means we see this feature at middle troposphere. We also see this feature at the upper troposphere. So in that sense, Paley and Hoskins, they also induced this pattern using the potential temperature gradient reversal. So here's this diagram is from the paper in 2003, indicating how the blocking occurs or what typical pattern looks like. So this dashed line is the typical climatology, which indicates westerlies in the mid-latitude. But this solid line, thick solid line, indicates a blocking pattern, very typical. Over here we have anticyclonic blocking. Over here, cyclonic blocking pattern. So typically we will have a high pressure system in the north, but low pressure system in the south. This is a typical one in the Atlantic and Europe. Okay, very typical. So if we want to have some dry conditions, we usually see that in the high part, in that cyclonic pattern part, which is give us a large scale subsidence, etc. And we see drier and warmer conditions over here. But in this part, we might see more wet or cooler conditions, right? So it's a background. We'll see later that this situation is not always true. Well, this one before that shows us the frequency of the blocking distribution by this index developed by Paley and Hoskins. Here I want to show you that this is the instantaneous statistic of the blocking patterns by as much as 30% for all season in the over the Europe 0-degree meridian, right? It's about 30%. But over United States or North Pacific, it's slightly over 15%. By this index, which is most dynamical and trustworthy, the frequencies over the North America is just about 50% of the EU. Okay, from this index and based on the typical definition of the blocking. There's also some other indices, such as based upon the 500 millibar potential gradient, potential height gradient. With that index, we can get even smaller frequencies over this area, impacting this area. And there's possibility to shift much westwards all the way to the ocean. So the actual events in these type of indices, we see very, very small number of cases. Why could that be possible? One reason is that the typical blocking index does not consider persistent ridges, such as this one. This early, if you look at the contours, it's just a ridge. It's open ridge, not blocked yet. For this one, very similar, if you see here, it's a ridge, not a blocking pattern yet. Even over here, it's just like an omega blocking pattern. It's a letter omega pattern. This is a typical, very typical in the northeast Pacific impacting North America. So there are two types missing in the traditional index. One, persistent open ridges. Second, immature omega blockings. Their number is very large, not just small. This one shows the whole event based on our tracking algorithm, which includes both open ridges and also the immature omega blockings. It lasts over 20 days. But if we use their index or indices, the persistent time is definitely shorter than 7 days or some, or even broken. So which means we got to take them back when we consider the impact of this type of persistent patterns to the extremes. So there's more frequency in the North America is because the persistent open ridges were ignored, simply. So we tracked all this back, and the paper is in revision, 2 months review. And this figure shows us during the DGF season, we see much larger frequency of these persistent patterns in the Northeast Pacific. The center is above 36%, even larger than the center over the Atlantic and Europe. Okay, we're not talking about classical blocking again. We're talking about blocking highs, including closed highs and open ridges. Both of these two types of high systems will cause exactly the same drying condition over the ground. Again, also very different from the previous index. If we consider the omega blocking, also persistent ranges, we have very large occurrence frequency over the United States in summer season, which is very important because under any range control over that area, particularly over the North United States, we'll see very hot conditions. So this is the reason why we need to consider blocking patterns when we discuss heat waves, droughts, especially to discuss the extremes. So statistically, how are we going to do this? How are we going to investigate extremes itself and the possible contributions from all these persistent patterns? So I'll give you next some statistical background, which is again background. Extreme events are rare. They're very rare, although they're not rarer than a jackpot Powerball. They're rare. They have a very low probability to occur. Also, statistically, they're also located at the tails of distribution and very, very less sampled. So it's always a challenge to understand why these rare events will occur and when and where they will occur, strike again. So we need some statistical tools first to get their distributions. Our regular approaches such as correlation, regression, or even composite analysis are less effective to extremes. Fortunately, we have some statistical theories which can help us investigate the extremes. For those extremes, such as extreme droughts, such as extreme heat waves, if they're non-degenerate, which means we're not seeing one number all the time, which is the case, they are non-degenerate. And also they are independent and identically distributed. Independent means this extreme is not dependent on the previous one or next one. They're independent first. And also they are identically distributed, means they are the same thing. We're talking about droughts. All extreme droughts should be distributed identically. We're not mixing these droughts with others. So in that sense, we're good. We're good in terms of independent, identically distributed. But there's some exceptions later. I'll describe that to you. But so basically, for all the extremes, we're talking about basically will mean this condition. They are. So once they are, we can use two similar distributions to fit these extremes. These two extreme distributions, the first one, if the three extremes are selected as a maximum block, such as the maximum heat wave index over that period, and then the maximum of each year. You can imagine that each year we get one value. This year we get one value. Next year we get one value. And for each year we get one value. All these values yearly, maximum of a spatial domain, they are independent. They are identically distributed. So in this case, it's a block maximum. These extremes follow the generalized extreme value distribution. I'll show you moments later the PDF of this distribution. There's second type. The second type means, okay, we have two little samples to do the block maximum. We can only do the exceedance over some threshold. For example, for the extreme heat wave, if our observations are too short, such as 10 years, if we do block maximum, we get 10 points. Too little to do the distribution. What if we need more? We need more. We can just move the threshold somewhere, which will give us more samples for the distribution. Such as for the 91-degree threshold, it's good. We use 91. If we consider 1012, there are too few cases. We just drop the threshold a little bit, such as 100. Then we get more points. We exceed that threshold, right? So we get more samples. But this approach immediately brings out the possibility that the exceeding points are not necessarily independent. We might get 2 points consecutively. They are not independent. So in that sense, we need more statistical tools to deal with those situations. We have that. So this is the second one, basically based upon the points over threshold, which is POT. Their distribution follows the generalized Pareto GP distribution. Here are the two the examples showing how block maxima POT works. Extreme values over here distribution. The block maxima we divide into different blocks. We take the maximum of each block as the extreme value. That's one way. Second way, we put a bar over here as threshold. Any points above that bar will be considered. Immediately you see that we could have points dependently collected. Degenerate, as I just explained, as long as we're not doing one value all time, it's good. So here's a CDF for the GEV, which is generalized extreme value distribution, good for block maximum. 3 parameters here, very important. One is mu is called location, Z is a variable itself, of course. Mu is a location. Sigma is a scale, always positive. Theta is the shape. The shape means we have a distribution, will give us different shapes. It's basically a EXP function, right? So theta different, could be greater than 0, give us a distribution. Could be 0, give another distribution. Could be negative, give a third distribution. So all these 3 distributions have a name. Either Frechet when the shape parameter is positive, or Weibull when the shape parameter is negative, or 0 as a Gumbel. It just gives us a shape of the distribution, nothing special. Again, this distribution have an equation each self. So analytically we can get the distribution. But in reality we have all the scattered points for the extremes. All the task we need to do is to fit our isolated points with the distributions to see which one fits better. Another one, very important to the extreme events, is return level. Return level means, okay, for this event, such as the drought in California, how many years averagely we can see another one like that? That's return level, right? Or even for the Sandy, that case, that hurricane hit the other eastern United States. How many years later we could possibly see another one? So this is a return level. For the GEV distribution, because we're taking the block maximum, such as Heatwave annually, if we give a 5% chance for that event to occur, which means we'll get 20 years to see that again. 5% yearly, we get 20 years to see that again. That's 100 divided by 5. If 1% chance, that would be 100 years return level. So it's really straightforward to define return level if we're talking about block maximum annually. So it's really understandable for return level for that. We basically analytically will determine the ZP where it locates. The P is the probability of a quantile for that event to occur, and then we take a logarithm. Then we get the distribution of that return level in terms of log probability. Then we see the linear distribution when the shape parameter is 0, which is Weibull. Or then we see different types. If it's positive, we see the concave. It's a Frechet type. We could not get an upper bound. If it's negative, we get an upper bound. It's Weibull. So analytically, it's easy. It looks very complicated, but it's actually the return level associated with the point. The second one, I'm going to skip the second one because the 2 cases we discussed about extreme, all about block maximum. So the second one basically is a GP distribution, very similar to the GEV distribution. All the three parameters, different distributions. Also this tail distribution and the return level is a little different because exceedance of level again. And also it requires a Poisson distribution to be combined to determine the return level. I'm going to skip this again. So stationary versus non-stationary. Stationary means once we have these extremes distribution, they're not going to change with time. It's stationary. Non-stationary, we have global warming. We lift the temperature. For heat waves, we see more severe heat waves. So that's non-stationary. Also, if we include the blocking patterns, we don't have blocking pattern, we have extreme. Another case, we have the blocking pattern, we have another extreme. These two distributions are different. They are non-stationary. So we need to consider non-stationary case to incorporate the trend patterns as covariates into those three parameters. Usually we only consider the first two, which is the location and the scale parameters, to see whether we incorporate these covariates to get a better fit. If we get a better fit, means the included covariates will contribute to the distribution. So that's a basic logic to do this statistic. So first, we need fit. We need to fit the extremes with any distribution. Next, we include the covariates. So these are two steps. And then we fit the maximum time series. We get parameters. How are we going to know those parameters are significant in terms of statistics? So we need to consider first how to estimate them. There are several approaches. Here we only use a maximum likelihood estimate, which means we have those three parameters. We based on this equation, this likelihood is simply taking logarithm of the PDF of that distribution. But we cannot get the analytical solution to this one. We can only do them numerically. We get the best possible parameters of theta, of sigma, of u. Then we get, okay, which distribution could be better fit. So once we have that, we can also get a significant band or range of each parameter. In that range, anyone could be good. But the one we selected maximize likelihood. That means it's maximum likelihood estimate. We need to fit the original extreme time series, give us the distribution. Later, we're going to include more covariates. We will have at least two distributions. Both are probably related, similar. Which one is better? So we're going to need a test. We're going to need a test to tell us which one is better. This test is named likelihood test. Likelihood ratio test. It determines whether the two distributions we get by not including the covariates or including the covariates could be better. So it determines whether these two distributions are significantly different at level, mostly at 5%, which is alpha level, by a chi-square distribution. Okay. So if we the computed p-value is more than alpha, which is 0.05, then we say, okay, these two distributions are significantly different. What does that mean? It means if we fit the original time series, we get distribution such as the Weibull distribution. Next time, we include the trend as the covariates. We get a second one. These two distributions, compare them under this test. Fortunately, we get us more than 0.05 p-value. Great. We can conclude, after including trend as a covariate, we get a better distribution, which means statistically, the covariate in this term, time trend, contributes to this distribution or to these extreme events. Okay, we're going to fit two. I'll use 10 minutes to go over these two extreme events. For each one, we're going to fit the original time series, and then we're going to include PNA, include NAL, include blocking, include trend each time, or combine into those two parameters to get a fit, and then compare whether after including those covariates we get a better fit, and whether that is significant statistically. Okay. First one, I just showed you moments ago. Here's the time series, original time series. It's a maximum PDSI over California, but during only the first 4 months of a year, from January to April, we all know that California have a climate scheme. It's a Mediterranean type. Its rainy season is during the cool seasons. Okay, during the summer season, it's hot and dry. It's basically dry. So we use those 4 months to derive the PDSI as a reversed, -1 times -1, which gives us positive numbers, extremes to indicate extreme droughts. Okay, again, this is a maximum again. Maximum means it's a block maximum. So can fit it basically with the GEV distribution. This is how we fit it. The left top panel shows a QQ plot, quantile plot. The X is from the model quantiles, which means we use this fitted model, we get quantiles. Vertical coordinate is from the empirical quantile. We just divide the extreme values in different quantiles. We plot them. The idea is to get straight line between these two. If we get a pure straight line, it means we'll get a perfect fit. But it's not possible because our samples for this GPDSI is limited. Analytically, we have unlimited number of points. So they are pretty much straight, which shows, okay, in terms of QQ plot, the fit is good, but not enough. We're going to see more. So we use the MLE method I just described. It's a maximum likelihood estimate. It gives us the 3 parameters. Location is nearly 5. Scale is 1.95, always positive. Most important parameter is the shape. It's negative. Again, it's a best one estimated. It means we get a Weibull distribution in this case. Okay. With this distribution, we immediately can determine the return level, such as we get 35-year return level at 10.7, and then 40-year return level at 10.88. It's a PDSI, extremely drought. If you go back to look at this curve, only recently we saw 10.85. So that corresponds to 35 to 40-year term, which means we could see that in about 35 to 40 years later, or at that range. So this is first fit. We just fit the original time series. Next, we're going to include each of them one by one. I did not show the trend here. Trend itself is embedded in the time series. If you see this one, we have the trend as the green one. We'll include it later. But for now, we need the 3 time series to be included. And each time we do one. First one, we do the blocking for the California. Originally, we discussed how blocking could impact it. So this time, we include the blocking time series into this fit. And we get this fit to compare with the fit we just had. Compare these two whether they are significantly different. If they are, great. Meaning that blocking does contribute to the drought, extreme drought. Yes, it is. So the likelihood ratio test results here, we have the alpha at 0.05. We have the p-value is much more than that value. Means statistically it is significant. Okay, which means after we incorporate the blocking information into this extreme time series, we could get a better fit. Okay, for the return level, it's changing now. Because it's not stationary, the previous feed assumes it was stationary. But now, after we incorporate any covariates, it's not stationary anymore. It gives us change in return level. For now, we see that the case a couple of years ago is actually below 20 years. What does that mean? If it's stationary, not changing with time, not including blocking here, we're going to see similar events at about 35 to 40 days. Now we're going to see it for about 20 years, more frequent, right? With blocking, we see similarly severe drought in California more frequently. This one, we're going to look at whether the trend is significant without considering anything else. Only consider the trend in the location parameter. Yes, again, we get a significant different distribution from the one we did not consider trend. The p-value here is way much more than 0.05. Okay, again, give us, after we get the trend, we will see more frequent, similarly severe event, drought event over California. Again, the green line here, I don't know whether you can see that, it's for 20-year return level, indicating the event a couple of years ago is below 20 years, suggesting we're going to see that less than 20 years in the future, similarly severe event, if we consider the trend. For the NAO, after the trend, After the trend is included in the location parameter, we continue to consider whether NAO can be included in the scale parameter. Then we get a distribution. The third one, we compare this one with the trend one, with the one with the trend. Yes, again, this one is significant, different, suggesting that, okay, first we consider trend. Second, we also need to consider NAO. And consider this both patterns together, we get a better fit. We also did some other ones, such as PNA. But PNA is slightly larger than 0.05, but statistically we have to reject it. We consider it marginally significant because we see the mixed patterns for different past years for the PNA, right? That agrees with the distributions. And also we're using either PNA or NAO as a covariates for location parameter. There's no distribution could be significantly different from the GV0. Means if we consider PNA or NAO alone without considering trend, we cannot get a better fit, which means themselves alone cannot contribute so significantly to the CA drought. The next one is about extreme heat waves over the central United States. Here's the time series we want to fit. The one I indicated here back in 2012 is a 100-year level. I'm going to just tell you the results. First one, we fitted the original stationary time series. We get the 100-year return level at 153. Again, it's a Weibull distribution. And the extreme value over that year is larger than 153. So it's a 100-year level. It's really scarce. It's really rare. Then we fit this time series with three covariates. First, we fit the trend, and it's significant. And give us return value now. Again, that year still at about 100 years. But the overall return level is dropped, which means we will see more frequently similar events. For the blocking, also significant, but again with the trend this time. But for the PNA and NAO, no matter we include either of them into the location parameter or in the scale parameter, after including the trend, none of them is significant, which means when we talk about extreme heat waves over the central United States, either PNA or NAO does not matter too much. Summary, as I just said, and I think future research directions will be to do the similar analysis over larger domains, even on grid points or location by location in the United States or over other areas in the world. And particularly more analysis is probably necessary on the potential physical dynamic mechanism associated with such changes. And also another very important direction is about climate change projections from numerous climate model simulations, how these things are going to change, fit them. So with that, thank you. And here's a quiz from my daughter's homework. Anyone want to figure this out? All right, thank you very much. Any questions? Yep.
I was just wondering, you didn't sort of specify. So when you sort of include the block, what does your block index actually include? Because, for example, PNA, we know that we have a monthly mean PNA, probably that's what you
yes.
include. But for the block, so the number of days, or you have included the number of days and amplitude, or things like that? That's
really a great question. I need to clarify here more. So it's all based upon this plot, the shading area in that plot. Short words, it's a expanded or impact area of blocking pattern. We see the shading area over here. It's all covered by the range. Okay, we have a very good way to figure them out, which points should be included, others are not. So all the index are based upon this shaded area first. Second, we have a box. Because we're discussing two specific regions, for the California region, we took the box closer to that, also include that region, but a little lower. So include a little more blocking patterns to these lows. Because sometimes we see ridges, they're not included, but they're actually inside the ridge. So that's one definition for the box for the drought case. For the heat wave case, very much similar. Also in this shady area, but this time we'll go a little further north, such as 35 to 55. The reason to do that is because during summertime we see the subtropical high. They're not blocking. They are not so strong to be detected by our approach, but they're there. So in this case, we trying to do the blocking. We do a box, including first the area we want to consider. Secondly, we include a little more northward. So basically, it's a box around here. Turning here. So then we get time series. The time series for that blocking, each blocking could persist for more than 2 days. We could give a stronger criteria, such as 4 days, 5 days, 10 days even. But some of the blocking do occur or do last for 2 weeks or even longer. Most of them 2 to 7 days. So with that, we get similar time series I showed you for 2 different cases. Great. Great. Lunch? Okay. Thank you very much.
It actually coincided